Good evening. Welcome to the 10th live session of Fundamentals of Additive Manufacturing Technology. So today we'll be discussing on powder feed based additive manufacturing and the process parameters. So basically it will be upon the nozzles and applications and different types of some process parameters used. Okay, so let's start with the questions. So, which of the following are advantages of discrete coaxial nozzles in powder feed based additive manufacturing process? Just So here, as we discussed last the time, there are different types of nozzles: discrete coaxial nozzles, continuous, which we have already discussed. I'll again share the slides. So out of these, which of the following are advantages of the discrete coaxial nozzles in powder feed based additive manufacturing processes? So for the discrete coaxial nozzles, as we know that we had various design consideration for the discrete coaxial nozzle, like ensuring the area of overlapping powder stream, correct standoff distance from the substrate, and when it proper injection radius which is positive to the standoff distance and powder mass concentration. Uh, these are some of the design considerations. So, based on that, there are various advantages and disadvantages. Okay, so the advantage of the discrete coaxial nozzle is the ability to manipulate carrier gas flow rates and flow velocities for individual powder stream, and also the omnidirectionality beyond 45 degree can be easily restored by increasing the drag velocity of a carrier gas. So both are the correct options. When suppose this is a region of particles. Now this is the particle region for low particle density. Now this head, there will be a head tilt. This is the inside this, there will be a head tilt. This renders this continuous coaxial nozzle, and which makes it non-omnidirectional. To counter this, we have the discrete coaxial nozzles which have the omnidirectionality feature, which is a very important. Take the head tilt can be accommodated. Head tilt can be accommodated in discrete coaxial nozzle. This is not possible in continuous coaxial nozzle. That is, it is non-omnidirectional. So omnidirectionality is a very important feature of the coaxial of the nozzles. And next is ability to manipulate carrier gas flow rates for individual powder streams. So in here what happens is, like with increased density of the powder on the bottom than in the top, a head tilt of continuous coaxial nozzle over an angle, this stops, but in discrete this problem is not there. So this is the main disadvantage of discrete coaxial nozzles. Now if someone is doubt for this, what are the different types of nozzles, we can again you can again refer to the last week's class where we have discussed all the types of nozzles. Moving on to the next question. Which of the following statements are correct for efficiency of nozzles in powder delivery system? Okay, so in the coaxial nozzles, the efficiency can be as low as 30%. Whereas for, and here the comparison which we are making is between the central feed nozzles and the coaxial nozzles. So, and the central feed nozzles, the efficiency is above 80%. So this is another advantage of using central feed powder delivery nozzle. What is it? It is the minimal divergence of the powder stream. Now, the central feed nozzles in the delivery system, uh, when it is combined with the Gaussian heat intensity, which we will again discuss what is a Gaussian heat intensity, this results in insufficient heating at the edge of the melt pool and excessive heating at the center. Consequently, what happens is there is a lack of fusion with the substrate at the edges and excessive dilution at the center. So, this is one of the, this is one of whatever I said, this is one of the um, another advantage of central feed nozzles. Okay, so according to this, the correct option is option A. Central feed nozzles is much greater than the coaxial nozzles, and that is why it is also preferred at some places, because it has the minimal divergence of the powder streams is very important. So here also the same figure we can refer. This is for the continuous coaxial nozzles. Okay, there is a head tilt. Here is a head tilt. But in the discrete coaxial nozzles, there is no head tilt. Okay. Any doubts till now? Okay. So I shall proceed. Why are gas-free delivery nozzles to be used with EB as a heat source? EB is electron beam. So this powder feed based delivery system, they have we have various process parameters like powder injection angle, mass flow rate, particle velocity, feedstock selection, stream characteristics, shield gas, omnidirectionality, smart powder delivery nozzles, and gas-free powder delivery. So now this use of electron beam requires a vacuum environment, which is written here. Okay, so here carrier gases cannot be used for powder feedstock delivery, powder feedstock handling. So that is why we use gas-free powder delivery nozzles, because it requires a vacuum environment. Now, this why we need this, because here we need to develop gas-free powder delivery nozzles, which needs to be used in along with electron beam as a heat source. And these are require feedback control, high flow mass rate to prevent melt pool oxidation. These are some other functionalities of powder based delivery system. So I'll just write. Okay, so what happens, we'll also discuss what happens in a closed loop feedback control, high mass flow rate, how it is obtained, and how melt pool oxidation is prevented. So this high mass flow rate, I'll just summarize it. High mass flow rate, this is associated with surface roughness and track porosity. And closed loop feedback control, closed loop feedback control and mass flow rate. These are also some of the other features. I just want to confirm, is it audible to all? Now, this closed loop feedback control, why it is required? Closed loop feedback control. This is required for fabrication of smart powder delivery nozzles. Now, what happens here is there are multiple inputs with which we can adjust the feed parameters in accordance with the system. Multiple inputs are provided which can be adjusted with the delivery system. Which can adjust its feed parameters the delivery system. Next is melt pool oxidation. So what happens is why is melt pool oxidation created? Melt pool oxidation is prevented by shielding gas. So what happens is additional provision of shield gas is provided for protection of laser optics from metal fumes and powder particles. Additional provision of shield gas is provided for protection of laser optics from powder particles and metal fumes. Metal fumes. So with this we also discussed some of the prime features of the powder delivery system. And apart from this, we also have the smart powder delivery nozzles, omnidirectionality, which you already discussed, proper feedstock material selection, such as aluminium, copper, and stream characteristics. Particle velocity should be low for increased catchment efficiency, and the powder injection angle, it should be low to support a longer depth of focus, to promote high deposition efficiency. So these are some of the this is some of the basic features, primary features of the powder delivery system in powder feed based additive manufacturing process. Okay, so moving on to the next question. What happens when the dilution ratio, okay, just ignore this, dilution ratio alpha greater than 30%, alpha is greater than 30% in laser cladding. So dilution ratio is defined as just give me a moment. So dilution ratio, it is defined as alpha is equal to delta by beta plus delta into 100. So now we have to find out. Now this dilution ratio is the optimal range for dilution ratio between the first layer and the substrate is 10 to 30%. Optimal range for dilution ratio between the first layer and substrate is 10 to 30%. Now when alpha is greater than 30%, keyhole occurs, and alpha less than 30%, lack of fusion is there. Now we'll understand what is this alpha and delta, delta and beta. So suppose this is a deposited bead and this is the substrate, and this is the substrate. This total shaded area is the substrate and this is the deposited bead. Now the height, this is the beta. Sorry. Now from here is half. From where cover it is the this first layer. This is the beta and this is the delta. Okay. Now and this ratio is delta by beta plus delta into 100. This is the dilution ratio. Now these are some of the defects: keyhole and lack of fusion. The correct answer is Answer B, keyhole. Now, what happens is usually there is a parameter, global energy density. Okay, it is used to investigate the interlayer and interlayer porosity due to lack of fusion and keyhole. Now, region with the low global energy density, these are subjected to lack of fusion induced porosity, and the region with high global energy density, these these are subjected to keyhole porosities. Now in the slides we can see various examples of keyhole and how this lack of fusion is this is visible. This can be better shown in the images in our lecture notes on the videos. Okay, so moving on to the next question. Pneumatic feedstock power handling system in the powder feed based additive manufacturing has which of the following features? So this is the direct question. So for this, the correct options are options B, C, and D. Only the convective cooling of the melt pool due to use of inert gas is not for pneumatic feedstock powder handling system. Now we will discuss a little bit on pneumatic feedstock powder handling system. So what happens? So there are non-pneumatic and pneumatic nozzles. Now, why we have this when we have this non-pneumatic feedstock, non-pneumatic nozzles. So why there are? This is a various. We have various popular designs like we do not maintain a concentric laser beam and where vibration applied through water bath through subwoofers, and there are like PZTs on a single mount, concentric laser beam, and various other things. Now for this what happens is in the powder feed handling system of pneumatic feedstock, we have poor surface finish on the deposited track due to high particle velocity. So as we know, I have already said that a lower particle velocity uh, comes from a increased gives a increased catchment efficiency. But here we have a, a higher particle velocity. Now also here we have entrapment of inert gases which leads to porosity. And with the pneumatic powder feed bed additive manufacturing, we cannot fabricate functionally graded materials. Now functionally graded materials are materials which vary uh, along the longitudinal direction or the along the axial direction with respect to their density, uh, thickness, cellular size, which are some of the major functionalities. Now this using this pneumatic feedstock powder handling system, we cannot fabricate FGM materials. But now in this we this is for the pneumatic feedstock. And again for the non-pneumatic, which I already said, we have various different setups, popular setups. Now why is the need of the non-pneumatic? Like there is a comparison also between the pneumatic and non-pneumatic, pneumatic and non-pneumatic powder delivery nozzles. nozzles. Just like sample cross section. This can be, this is according to a literature paper by Wong et al. 2011. So here the sample cross section is 8.6 millimeters square and here it is 8.09 millimeters square. Total porosity, this can be 0.015 millimeters square, 0.04 millimeters square, and surface roughness is 2.14 micrometer and here it is 14.25 micrometer. So you are seeing a great value of surface roughness in non-pneumatic powder delivery nozzles. Now this non-pneumatic powder delivery, pneumatic powder delivery nozzles is also known as gas assisted nozzles. Okay, which we have already uh, discussed throughout. So moving on to the next question. Which of the following is an application of, okay, I just missed one more question. Vibration assisted powder delivery nozzles has which of the following functions? So the correct options are option A, C, D. Acoustic vibration can be used for powder delivery nozzle, ultrasonic vibration can be used for powder delivery nozzle, and water bath can be used for the uniform application of vibration to the powder delivery nozzles through a sonotone. Now we will just briefly discuss what is a vibration assisted powder delivery nozzles. So here use of mechanical vibrations are done to transport granular material So briefly on this we had discussed some last time also, like it is very popular in agriculture and food processing industry. So this is now in this setup we use the acoustic vibration and vibratory, and also when with this process we can also produce the functionally graded material. This can be done by the vibratory conveyance method, and ultrasonic vibration can also be used for powder delivery, and the water bath medium can also be used, but carrier gases are completely different. So this is a gas assisted is already another type of powder delivery system in powder feed based additive manufacturing processes. So as we already know, then the delivery systems of powder feed based additive manufacturing, we have different classifications, just gas assisted, vibration assisted, and gravity driven. Out of this, vibration assisted is one of, and we also discussed this gravity driven last class. Now gravity driven, what it is highly used. It is similar to the vibratory method, but like these setups are very this is very rarely used because of the phenomenon of jamming, which we again discussed in last class. Okay, so moving on to the next question. Which of the following is an application of powder feed based additive manufacturing process? Laser cladding, alloying, functional grade material, part restoration, all. The correct option is all. So now this powder feed based applications, these have various applications, which this can be used for manufacturing very large components, functional graded material, laser cladding, surface learning part used to grid stiffened structures. So out of this, and one more also is there. Application grid stiffened structures. So we'll briefly discuss on what are each methods. So laser cladding, this is done to modify the properties of the base material surface using a similar or dissimilar material by melting in order both that similar and dissimilar material, these can be melted similar and dissimilar material can be melted in order to obtain a new surface with the desired properties. Now, part restoration, this is done for repairing purpose. Now the component is transformed into a digital format, into like mesh, particularly into a mesh representation, and this is then from the mesh we get the CAD input, which can later be analyzed for we can analyze how to repair it and toolpath planning. So first here, conversion to mesh representation, then CAD input is provided, then analyzed for extracting the repair volume and restoration and toolpath planning. And next is we have functionally graded material, which I already said that here we can vary the various parameters like texture, porosity, porosity, some terms relative density, grain size, and cellular grain size, or also we can here take it the unit cell size, and there gradually we can increase or decrease longitudinally or axially, whichever direction we require. So this will lead to various changes associated with at least one property. So, and it is usually noticed that obtaining functionally graded material along the build direction is very more challenging than the functional graded material along the other build directions. Okay, so next is we have the last one is grid stiffened structures. Now, this grid stiffened structures are like some plates or shell, some plates. These are layered with some patterns of ribs in specific geometric configuration. So these are usually used in very payload carrying capacity with, so that there we can reduce the structural weight. What how it is done is, like, why it is done is, it is usually done to absorb the vibration and provide high stiffness for other members, other machine components. So uh, it is uh, it is usually, this process is usually tried to be done by 3D printing processes. Okay. So these were the questions. So any further questions? We still have time, so we can discuss. So these questions were quite similar to the assignment questions, the second half of assignment questions. Okay, so if there are no further questions, I'll still wait for some more time. So with this, we actually today covered the powder feed based additive manufacturing processes completely. Next, we are left with electron beam powder based manufacturing, binder based powder manufacturing. So these will be covered in the next coming two classes. One class for electron beam powder based manufacturing and another for binder based powder bed manufacturing. These are the last two classes left. So after that, we have the exams. So please let me know if there are any further questions or doubts in the assignments, or any other questions or queries regarding the uh, exams or anything. Okay, so if there are no further questions, we'll end the session. Thank you for attending the session, and let's meet next week. Okay. Thank you.